In 2017, AMD shipped a server chip that was, by its own engineers' math, deliberately about 10% too big. And according to AMD's own internal yield model estimate, it cost roughly 59 cents on the monolithic dollar. Here's the part nobody explains: how being wasteful on silicon made the silicon cost less, and why the high-end CPU business eventually copied a bet that for decades had mostly been treated as a compromise. To understand the bet, you first have to understand why a bigger chip costs more. And it is not for the reason you think. A defect is a random event. It happens somewhere on the wafer. If your die is small, a single flaw ruins one chip out of dozens. The rest of the wafer is fine. But if your die is enormous, that same single flaw can sit inside the only chip you were trying to bro. One speck, one dead die, one ruined block of silicon. And this is the part that bends intuition. The relationship is not linear. AMD's own white paper states it plainly. There is an inverse exponential reduction in yield with larger die size. Double the die and you do not lose twice as many chips. You lose many more than twice as many. Bigger dies don't cost more because they use more silicon. They cost more because they are more likely to be born broken. Think of it like glass. A single large pane is one bad strike away from being worthless. Score that same pane into 4 pieces, and a single flaw ruins a quarter of your material, not all of it. That is not a cleverness argument. It is a probability argument. And in 2017, AMD betted server comeback on probability being more forgiving than perfection. There was also a hard physical reason. AMD's 4 Zeppelin dies added up to 852 square millimeters, which the company noted is too large to expose in a single optical lithography shot. Even if they had wanted one giant die, the physics of the light they print chips with was telling them no. So if probability and physics were both whispering go small, why did the entire industry spend 50 years going as big as it possibly could? The answer is the cost of gluing the pieces back together. After Bulldozer, AMD entered the mid-2010s trying to rebuild its server business from a weak position. For this story, the constraint is the only thing that matters. AMD did not have the luxury of designing a giant, bespoke, monolithic server die to fight Intel. It had to be cheap. So AMD designed one modest die, codenamed Zeppelin, about 213 square millimeters, 8 cores, and used it everywhere. One Zeppelin became a desktop Ryzen. 2 active Zeppelin dies underpinned first-generation Threadripper. 4, bolted together, became a server chip called Naples. This is the first half of the trick. AMD amortized the cost of designing that one die across its entire product line. Here is the number at the center of everything. AMD's white paper lays out the trade explicitly. A hypothetical monolithic version of that server chip, after removing the duplicate interconnect logic 4 separate dies need, would have been about 777 square millimeters. The 4 Zeppelin dies add up to 852, so AMD used roughly 10% more total silicon. And yet, using AMD's own historical yield model and production defect density, the 4 smaller dies came out to less than 60% of the cost of the one large die. They paid a 10% silicon tax to collect a 41% discount. That is the smaller die loophole. And because AMD was now spending so much less per working chip, it could afford to simply throw more of them at the problem. In AMD's own head-to-head comparison, the first Naples processor offered 45% more cores, 60% more I/O, and over double the memory bandwidth of the Intel Xeon it was measured against. It was not a faster die, it was more die, cheaper. But 4 separate dies do not behave like one die. Not unless you can move data between them fast enough that software never notices. So AMD rebuilt the old socket-to-socket interconnect to work inside a single package, and called it the Infinity Fabric.
Coverage of Naples reported about 42.6 gigabytes per second of intra-package fabric cross-sectional bandwidth. That is the glue, and glue is what the bet actually cost them. The bet had three costs. The obvious one, about 10% more silicon wasted on duplicate interconnect logic. The subtle one, a little latency every time data crossed between dies. And the one nobody mentions, packaging. Lisa Su herself flagged it. If each chiplet is placed on its substrate with 99% accuracy, a 3-chiplet product eats roughly a 3% yield loss just in assembly. You saved money in the fab and spent some of it back in the packaging house.
2 years later, AMD did something that turned a clever trick into a strategic weapon. They split the chip again, but this time by function, not just by area. The new chip, Rome, took the expensive compute cores and etched them on TSMC's brand-new, brand-expensive 7-nanometer process. But it pulled all the memory controllers and I/O off those expensive dies and dumped them onto a single, cheaper I/O die built on an older, cheaper 14-nanometer process from GlobalFoundries. The insight: put only the logic that benefits from the cutting edge on the cutting edge. Pay the premium where it earns its keep. Be cheap everywhere else. Rome also doubled what the fabric could move, 32 bytes read per clock instead of 16, and quadrupled the cache. 8 compute chiplets and 1 I/O die, 9 separate pieces of silicon behaving as a single 64-core processor, a package Intel's monolithic server strategy struggled to match at the same economics. And here is where the bet compounds. The reason the math only gets sharper over time is that advanced nodes are more expensive per square millimeter than the ones before them. So the penalty for a defect, the probability tax on a big die, gets heavier at exactly the moment the silicon itself gets pricier. Every node shrink makes big dies more likely to die on the line and makes dying on the line more expensive. The chiplet advantage is not static, it widens. By 4th-generation EPYC, AMD was gluing 8 compute chiplets around an I/O die, and the company estimated that chiplet approach alone avoided around 50,000 metric tons of carbon dioxide equivalent in 2023. What started as a budget compromise became the default way the industry builds big silicon.
Now, the strongest objection to all of this: multi-chip modules are not new. AMD itself glued together a 12-core server chip called Core back in 2010. Intel did it with the Pentium D. IBM built multi-chip packages decades ago. So the objection goes, AMD didn't invent anything. It just repackaged an old idea when node economics happened to make it favorable, and Intel adopted the same idea later anyway. Some lead. And there's truth in it. AMD did not invent the multi-chip module, but the thesis here was never about invention. It was about the specific, documented cost inversion. Core was a packaging convenience. Glue 2 dies together, ship more cores. Naples is the public case that matters here, a mainstream x86 server CPU where AMD published the yield math, showing that smaller dies were cheaper than one big one, even after paying the interconnect tax under modern node economics. Intel's later move to tiles is not evidence AMD got lucky. It is confirmation the math was right. So here is the bet restated. AMD won by betting that probability forgives what perfection punishes, that a chip deliberately built 10% too big in 4 pieces could be 41% cheaper than the flawless monolith it was supposed to replace, that the flaw in a big die is not a risk you engineer away, it is a tax you refuse to pay. And to be intellectually honest about it, what would change my mind is simple. Show me a monolithic design that matched the same cost per core at the same node without paying the area penalty. The public record does not show one. If you know of one, the sources are all on screen. Take a look
and tell me where the math breaks. Every number in this video is on screen with its source. Links are in the description. If you want the next one, the night AMD's foundry partner stepped away from the leading edge and forced the Rome split, that is next.